Example 4. Solve the equation y double prime minus 6y prime plus 13y equals 0. Solution. The auxiliary equation is r squared minus 6r plus 13 equals 0. By the quadratic formula, the roots are r equals 6 plus or minus the square root of 36 minus 52 over 2 equals 6 plus or minus the square root of negative 16 over 2 equals 3 plus or minus 2i. By equation 11, the general solution of the differential equation is y equals e to the power 3x times open c sub 1 cosine 2x plus c sub 2 sine 2x closed. Sidebar figure 3 shows the graphs of the solutions in example 4. F of x equals e to the power 3x cosine 2x and g of x equals e to the power 3x sine 2x. Together with some linear combinations, all solutions approach 0 as x approaches infinity. See figure 3. We have g and f plus g, and f minus g. Initial value and boundary value problems. An initial value problem for the second order equation 1 or 2 consists of finding a solution y of the differential equation that also satisfies initial conditions of the form y of x sub naught equals y sub naught, and y prime of x sub naught equals y sub 1, where y sub naught and y sub 1 are given constants. If the capitals P, Q, R, and G are continuous on an interval and P of x does not equal to 0, there then a theorem found in more advanced books guarantees the existence and uniqueness of a solution to this initial value problem. Examples 5 and 6 illustrate the technique for solving such a problem. Example 5. Solve the initial value problem. Y double prime plus y prime minus 6y equals 0. Y of 0 equals 1. Y prime of 0 equals 0. Solution. From example 1, we know that the general solution of the differential equation is y of x equals c sub 1 times e to the power 2x plus c sub 2 times e to the power negative 3x. Differentiating this solution, we get y prime of x equals 2 2 c sub 1 times e to the power x minus 3 c sub 2 times e to the power negative 3x. To satisfy the initial conditions, we require that equation 12 y of 0 equals c sub 1 plus c sub 2 equals 1, and equation 13 y prime of 0 equals 2 times c sub 1 minus 3 times c sub 2 equals 0. From equation 13, we have c sub 2 equals 2 over 3 times c sub 1, and so equation 12 gives c sub 1 plus 2 over 3 c sub 1 equals 1. C sub 1 equals 3 over 5, and c sub 2 equals 2 over 5. Thus, the required solution of the initial value problem is y equals 3/5 times e to the power 2x plus 2 over 5 times e to the power negative 3x. Sidebar figure 4 shows the graph of the solution of the initial value problem in example 5. Compare with figure 1. See figure 4. Example 6. Solve the initial value problem y double prime plus y prime equals 0. Y of 0 equals 2. Y prime of 0 equals 3. Solution. The auxiliary equation is r squared plus 1 equals 0, or r squared equals negative 1, whose roots are plus or minus I. Thus alpha equals 0, beta equals 1, and since e to the power 0x equals 1, the general solution is y of x equals c sub 1 cosine x and c sub 2 sine x, since y prime of x equals negative c sub 1 sine x and c sub 2 cosine x. The initial conditions become y of 0 equals c sub 1 equals 2, y prime of 0 equals c sub 2 equals 3. Therefore, the solution of the initial value problem is y of x equals 2 cosine x plus 3 sine x. A boundary value problem for equation 1 or 2 consists of finding a solution of the differential equation that also satisfies boundary conditions of the form y of x sub naught equals y sub naught and y of x sub 1 equals y sub 1. In contrast with the situation for initial value problems, a boundary value problem does not always have a solution. The method is illustrated in example 7. Sidebar, the solution to example 6 is graphed in figure 5. It appears to be a shifted sine curve, and indeed you can verify that another way of writing the solution is y equals the square root of 13 times sine open x plus phi closed, where tangent of phi equals 2/3. See figure 5. Example 7. Solve the boundary value problem y double prime plus 2y prime plus y prime equals 0. Y of 0 equals 1. Y of 1 equals 3. Solution. The auxiliary equation is r squared plus 2r plus 1 equals 0, or open r plus 1 close squared equals 0, whose only root is r equals negative 1. Therefore, the general solution is y of x equals c sub 1 times e to the power negative x plus c sub 2 times x times e to the power negative x. The boundary conditions are satisfied if y of 0 equals c sub 1 equals 1, and y of 1 equals c sub 1 times e to the power negative 1 plus c sub 2 times e to the power negative 1 equals 3. The first condition gives c sub 1 equals 1. So the second condition becomes e to the power negative 1 plus c sub 2 times e to the power negative 1 equals 3. Solving this equation for c sub 2 by first multiplying through by e, we get 1 plus c sub 2 equals 3e. So c sub 2 equals 3e minus 1. Thus, the solution of the boundary value problem is y equals e to the power negative x plus open 3e minus 1 close times x times e to the power negative x. Summary solutions of a y double prime plus b y prime plus c equals 0. Roots of, there's a columns. Two columns are roots of ar squared plus br plus c equals 0. The other column is general solution. The first root of a r squared plus br plus c equals 0 is r sub 1 and r sub 2, real and distinct. General solution, y equals c sub 1 times e to the power r sub 1 x plus c sub 2 to the power plus c sub 2 times e to the power r sub 2 x. Next line, r sub 1 equals r sub 2 equals r. General solution, y equals c sub 1 times e to the power rx plus c sub 2 times x times e to the power rx. Next line, r sub 1 and r sub 2 complex a plus or minus I beta. General solution, y equals e to the power ax times open c sub 1 cosine beta x plus c sub 2 sine beta x close. Sidebar, figure 6 shows the graph of the solution of the boundary value problem in example 7. Figure 6.